Hi everyone and welcome back to our dynamic programming series. We are here on Leetcode with our fourth problem, mean cost climbing stairs. Without further ado, let's get right into it. So let's see what this problem wants from us precisely. Now we are given an integer array cost where cost of I is the cost of the if step on a staircase. Once you pay the cost, you can either climb one or two steps. Okay, so this is from the get-go a tremendously important piece of information. Now, you can start either from the step with index 0 or the step with index 1. So even from the beginning, we are given the possibility to directly jump onto the first or second stair on the staircase. Reach the minimum cost to reach the top of the floor. All right, now we have a couple of examples here. Here we have a simple array with 10, 15, and 20. And since 15 will be the shortest path because we can directly start from the second stair and then jump two stairs on top of the staircase, let's say. So, okay, pay 15 and climb two steps to reach the top. All right, so we have to reach the following stair after the last one. So, very important piece of information here because we can reach the top of the staircase from the last stair or the previous to last stair. Now here we have a bunch of ones and 100s, and we have to output 6 because we can skip all of these huge 100 cost and extremely expensive stairs. So as you can see, we can jump from this one, to this one to skip another one here, skip the 100, go one step so that we can also skip the 100. And since we are on the last stair, we have finished traversing this array. Now, this is not a problem that, although it's tagged with the Fibonacci numbers, we will use that technique in order to come up with a solution. It's not exactly the particular old school Fibonacci algorithm. All right, so how does this go? Let's take the second example, and I want to reproduce it in our beautiful iDrew here. So we have 100. All right. So we're starting off with 1. Then we have 100, a couple of ones. Okay, 3 ones, another 100, 2 more, and 101. Beautiful. Now here we will use a technique that is very common among dynamic programming patterns, and that is creating an additional, at least theoretical array, exchanging the piece of information that we are storing. So what I mean by that is, reading again, once you pay the cost, you can either climb one or two steps. All right. And here the idea is the following. If you remember from the previous stair problem, we will be using the exact same logic here. So for example, if I know that I require X amount of money to reach this particular stair, and then I also know that in order to reach the following stair, I need Y amount of money, then I can precisely calculate how much money will I need, the minimum amount, to reach staircase Z. Because let's say these are the actual indexes of these stairs. So if I know that in order to reach this stair, I need X amount of money, and in order to reach this stair, I need Y amount of money, then in order to reach this one particularly, I will need the minimum amount between these two, so between X and Y, and then add this 100, because afterwards, if I want to start from Z, I will also have to pay this 100. So I will make the minimum out of this one, so whichever is the minimum out of these values, plus the 100. And this is how I come up with the minimum number of money, coins, unit, whatever you want to call them, required to reach this particular stair. And how are we going to do this inside here? Well, like this. Let's apply this logic to our beautiful vector here. So we are starting from 0. Okay, so technically at the beginning of the staircase, we can either start from the first one or the second one. So in order to reach the first stair, you'll have to pay 1, because if you are starting from 1, you also have to pay this particular amount. Now, if we want to start from 2, because we have no idea what the value will be, again, we have to pay this 100. Now, if we want to go to the third stair, we will use the following logic. We have no idea how much money do we have to pay to get here, because for the very first 2 stairs is the beginning initialization. Now we make the minimum of these values. So whichever of these values is minimal and is definitely the one, and then we add the cost of getting to this particular stair. Okay, because since we are getting to that stair, we have to compulsory pay this value, and then we can move on. Right? So no matter if it's optimal or not, we want to calculate how much money do we need in order to reach this stair. So its minimum amount between 1 and 100, which is 1, plus this 1, we'll get here a total beautiful cost of 2. Now, in order to reach the fourth stair, right, we will need to add 1 to the final result, okay, because it's going to be the cost of being on this stair, plus the minimum between the previous one and the previous one. So whichever of this has the lowest value will be added with 1, and we will get the value here. So being 2, 2 plus 1 will be equal to 3. And so we have found the minimum amount of money or coins that we will need in order to reach the fourth stair. Moving on a little bit faster, reaching the fifth stair, we will need to add 1 to the minimum of these previous 2 stairs. And since the minimum is 2, because if we want to reach these 2, we can start from 1, then go here, pay this price, and then pay this price, and reach this fifth stair. All right, just sort of a recap. So adding 1 plus 2, because it's the minimum between 2 and 3, we'll get here 3 as well. Right? Now I'm gonna leave you a couple seconds to finish the entire array, but I'm gonna finish along with you. Right. So if we want to reach this 6th stair, we have to add 100 to the minimum value of these previous 2 ones, which is going to be 3, and then we get the value 103. Getting to the 7th stair, we have 1 plus the minimum value between these 2, which is 3, so we get a beautiful 4. Continuing using the same logic, 1 with the minimum values of between 103 and 4, we get 5. Now between 4 and 5, 4 is the lower value. Adding 100, the price of being on this stair, we get 104. And right now, jumping to the very last stair here, we have 1 plus the minimum value between these 2, which is 5, and then we get a 6. And right now, because we have finally reached the last stair of the staircase, we want to jump on top of it. And jumping on top of it is actually the minimum value between these last 2 stairs, okay? Because we can either jump from here 1 step, or we can jump from here 2 steps, right? Because once you pay the cost, you can either climb 1 or 2 steps. So if we pay the cost to reach here, we can directly jump 2 stairs. But since 6 is way lower than 104, 6 will be our last answer. So will be the solution to this vector. As you can see, we have worked on this example, the second example, and we have the output 6. Right? Now, for efficiency purposes, we don't, and regarding this problem precisely, we don't need to compute this entire array. We drew it so that we understand, we have calculated now the minimal cost of being on each stair independently. But we don't need to remember all of those, although we will compute them. We will just need to, so we don't need to allocate that much memory. We can easier follow that logic using just two variables, all right? So we can initialize, for example, these two very first numbers with, let's say, behind 2 and behind 1, and then have a current variable here. So we are starting from the third stair, yeah, from the first stair, because the very first two we have already initialized separately, and then we compute. We make the minimum amount between behind 1, which is 1 stair behind, and behind 2, which is 2 stairs behind. Okay, we search for the minimum value between these two here. Then whichever is lower, we will add to the value of getting to this stair, okay, to its particular cost. And this will be the value of the current stair. And then we just have to update. We can update B2 to B1, B1 to our current, and then current will then be calculated for the following stair using the exact same logic. So the algorithm is more or less straightforward, and we can just continue this logic inside of a for loop up until we have reached the end of the vector, because here we will have current, here we will have behind 2, behind 1, and current will be out of bounds. And it's exactly what we want, because we want to reach the out of bounds section of the array. And when current gets out of bounds, we just need to return the new minimum value between behind 1 and behind 2, because since we can pay, this is the minimum amount of money that has to be paid in order to reach this particular stair. Once you pay it, you can go on top of our beautiful staircase, right? Now let's see how that looks, what that looks into code. So firstly, we will need to declare our beautiful behind 0 equal to cost of 0, or let's call it behind 2, whichever you want. All right. And then behind 1 will be equal to cost of 1. All right. So we just initialized here behind 0 and behind 1. We also need to declare current and index, which will be our variable for writing the for loop. Now, for our beautiful index equal to 2, do we need to tackle? No, we don't need to tackle edge cases, because if the constraint, so cost.length, oh, it's already greater or equal to 2, so it will at least run once, and even if it doesn't, it will just go to the final condition, so it's all right. And lower or equal to 1000, and also cost of I can go up to 999. And if we multiply this, yeah, we can store them inside of an integer, so we have no issues regarding memory. Now, index has to be lower than cost.size here, which will return the size of this vector, because cost is of type vector of integers. And then we increment the index after every iteration. Now, a few of you might be wondering, why am I using the pre-incrementation and not the post-incrementation? That is because the pre-incrementation is arguably slightly faster, but we will discuss that in another video. That's topic for another video. Now, we have to check here. So we have before 2, we have before 1, and right now we have to compute current. How do we compute current? Well, if you remember precisely, I'm going to delete this one. Okay. Current is calculated by finding the minimum amount between these two and then adding the cost of stepping on that stair. So let's compute the minimum amount between behind 1 lower than behind 2. That's the first case. And we don't need the brackets actually. And then the else is the exact same opposite. So if behind 1 is lower current is equal to behind 1 plus cost of index. All right, because if behind the if behind 1 is lower, current will be behind 1 plus cost of index. If behind 2 is lower, then current will be equal to behind 2 plus cost of index, right? Because so here is our indexing variable, okay, pointing towards the current value that we have not yet computed. So we don't know the 2 yet. And in order to reach here, we add 1 to the minimum between two values. All right, just as a way to recap. And now is the exact same formula right here, but now behind 2 is smaller. And also we have to update these variables. So behind 2 is equal to behind 1, and behind 1 is equal to current, right? Because after we finish computing this one, the index after this iteration will move on. So the current will move on to computing the next value. Behind 2 has to move here. Behind 1 has to move here. All right, so moving in front one variable. And we have updated everything. And right now we have reached, when index will be equal to cost.size, we will have reached the very end out of bounds that we talked about. And right now we just have to return the minimum amount from these two variables. So checking them, if behind 1 is behind 1 is lower than behind 2, we return behind 1. Else we can just return behind 2. Why is that? Well, because if this condition will be met, then we return behind 1. Else we directly go to return behind 2. We don't actually need to put that else there. And the code looks pretty good. Let's do a quick test. So running these two examples, we output it properly here and here as well. Now submitting our answer and see what Leetcode has to say about it, and we get 100% on runtime, and like almost 70% on memory, which is pretty good. Apparently, there are a lot of people that have quite a huge runtime, and in terms of space complexity, we are doing very well as granted. So I think I saw something weird, but nonetheless, taking over. Now, this was not a very difficult problem, but you have to figure out and understand exactly how to apply dynamic programming patterns in solving the issue. So following what the problem gives you every single detail, you have to find a formula, you have to find a pattern in which you can apply to every single step, iterating through those steps until you reach your particular answer. So always break the problem into smaller problems. Think of how you can calculate this value for the second for the third stair on your staircase. Then you just add a for loop, you just index, use the exact same formula, the exact same idea that you have found to calculate for every single one of the stairs. So once you figure out how to do this for one particular stair, you can generalize and do this for everything. Right? Thank you very much for watching. See you next episode. Bye.